Hello everyone, my name is Jordan Johnson from Group B, and this is our final demonstration for the smart parking system. Our group consisted of three computer engineers being Oscar Acuna, M. Ridwan, and Kyle Carpenter, and one electrical engineer being me, Jordan Johnson.
For our goals and objectives, it's to use the computer vision to detect cars passing through specific regions of the garage. We want LED displays to communicate how many total open parking spaces are available in that region of the garage. We want the system to be low power, but it isn't a high priority of ours since the system is not going to be battery driven. We're going to utilize Ethernet for communicating between the camera and the server as well as the sign display. The parking garage is going to be using a regional info system, as we're calling it. So, as explained earlier, we're wanting to display information in specific regions of the garage. So the camera will detect cars leaving or entering the specific region of the garage within view of the camera. It's going to then use that data and send it over to the database, which will then update depending on how many total spots are said to be in that specific region of the garage. If a car's entering, it'll subtract how many parking spots are available. If a car's leaving, it will add to it. And whatever value is currently there, it will send to the correct PCB that aligns with the display in the specific region we're wanting to update. We're also going to have a GUI application which will show that information on a broader scale so we can see multiple regions at once. And this is good for someone who's not in the garage but wants to know where availability is. For the system, we want it to have a max update delay of 10 seconds, with a minimum brightness of 1000 nits, and in terms of scalability, we want to be able to have 100 camera PCB assemblies. For accuracy, we want it to be at least 95% accurate when detecting vehicles entering or leaving. In the video, we're going to be demonstrating our camera's accuracy in detecting the vehicles, the system updating the database, and showing the LED, its different things it can display and how bright it is.
To begin our demo, we'd like to show you all the components that are involved. On the screen currently is our PCB, which has the debugger, LED matrix cable, and Ethernet splitter all connected to it. The PCB drives the LED matrix and determines what number is being shown to the drivers in the garage, and you can see the number being switched from 21 to 18 here. Moving away from the PCB and LED matrix, we have the rest of the system, which includes the power over Ethernet switch, the central server, the uninterruptible power supply, and our Oak One PoE camera, which can be seen on the tripod in the back. So first, we have a car leaving your row of parking spaces. The LED sign currently shows 48 spaces available, and once the car has left, we would want it to now show 49 spaces available. Our next case shows a car entering a row of parking spaces, and once this happens, we would want the LED sign to update from 49 spaces available to 48 spaces available.
Here we are showing the GUI updating. A car has just entered the parking row, and you can see how the number 413 goes down to 412 after pressing the refresh button. This is to indicate that there is one less space available for parking. In the live view section of the GUI, we can see on this table on the last row that the number -1 was entered by the camera to indicate again that there is one less spot available.
In these next couple of clips, we have multiple cars leaving and entering the row of parking spaces. You can see how the program that is running accounts for every single car, and the way it does this is with a vehicle recognition model that takes the coordinates of each vehicle in the video and notes whether it is leaving or entering that row. Entering means the coordinates of the vehicle have gone from the right side of the screen to the left side of the screen, and leaving means the coordinates of the vehicle have gone from the left side of the screen to the right side of the screen. In the next few clips, we have some edge cases that could have an impact on the accuracy of our system. The first one shows two cars entering and leaving at the same time, and as you can see, the system accounts for each car accurately. In the next case, we have a car that enters and then leaves the adjacent row of parking spaces, and you can see that our program does not account for this car since it is not monitoring that row. For our last edge case, we have people crossing in front of the camera, and as you can see, this does not affect the accuracy of our system, as we have made it to where it should only account for vehicles and nothing else. Now that we have shown you a demonstration of our system, we will now go into future improvements of our system and begin with the PCB. If we were to make changes to the design of the PCB in the future, we would consider using a switching regulator rather than a linear regulator. In our initial design, we had a 12-volt input into our PCB, and even though our design does not pull a lot of current and does not require something that is super efficient, our regulator would still get pretty hot since this 12 volts is getting dropped to 3.3 volts. This led to us changing our voltage input to a 5-volt input to counteract the heat that was let off by the regulator, which really caused us to spend more money on our design. Using a switching regulator would have given us more flexibility with the voltage input. It would make more sense for our design, since this is something that we would expect to run 24 hours a day and 7 days a week. The second improvement we would make to the PCB is exploring PHY chips made by the manufacturer of our microcontroller. We believe we would have had more success with this part of the project had we decided to use a different Ethernet PHY chip rather than the one that we are currently working with, which is made by TI.
For future improvements for the Ethernet, we could port over the lightweight IP stack over to the microcontroller from the ground up. This is another TCP IP stack, similar to what's provided by Microchip. However, it would take a while to port over just because there's not any existing APIs or drivers that would make it simple to get started. However, for Microchip, they have the Harmony 3 software, and this would allow us to port over their existing TCP IP stack more easily. But this was a problem that we encountered when working on our project originally, is that the Harmony software had a number of problems with generating code that would properly interface with our microcontroller. A number of pins would be disabled, and it required a whole lot of digging through all the code to figure out why each thing wasn't working, and ultimately that's what became the problem for us. However, with more time, we may have been able to get this working.
There are some improvements that we have thought of which would refine the performance of the computer vision part of the system. They would both enhance user experience as well as add finer functionality. One of the modifications we were initially planning was to be able to account for cars within the camera frame. In this picture, as you can see, these cars are in static positions. However, our system does not include them in the vehicle detection. Our suggestion is to set the return ID for each detection as unique and keep track of them. And as soon as the static detection's ID disappears from view, count the object and add to the label. The second modification would improve user experience by drawing rectangles around only the moving vehicles. Currently, the model is able to detect and draw rectangles around all the detected vehicles within the frame. It would be nice to see the rectangles around the moving vehicles only for better view.